All right. So the thought experiment. So let me redraw, or let me just grab hold of whatever was there. We just need the piston and cylinder. So let me grab hold of the piston and cylinder. Let me just drag it down. Just keep it ready over here. All right. So you start off, let me just write down the states. So this is state 1. State 1, where you have water at 20 degrees Celsius. So you have water everywhere. Then you heat it. Okay. So when you heat it, you say that there is a sensible heat transfer. Sensible meaning you can sense the temperature of the water changing. And so you all know from elementary school that m P delta T is going to be equal to the amount of heat transferred. And that is true in this case as well. So after heating, even when it reaches something less than the boiling point, there will be hardly any appreciable change in the volume. Slight change will be there in the volume, but nothing drastic. Okay, so after heating, it will, suppose this is at 80 degrees Celsius. It has absorbed a certain amount of heat, and now the water is at 80 degrees Celsius. This initial volume and this volume presently, they will be different. This volume will be slightly larger. Why will the volume be slightly larger? What is the
So,
property?
little
So
over
density,
I mean, in very precise terms, what property causes that? I mean, how do you define that singular property?
thermal expansion.
thermal expansion.
Yes, so it's the volumetric expansion. Volumetric coefficient of thermal expansion. Yes?
Yes, sir.
All right. So because of that, volume will slightly increase. That coefficient is so small, okay, it will not be even perceivable. Great. Now, this will keep on going up until you reach the boiling point at 0.1 megapascal. So remember that the pressure, somehow we are loading it with 0.1 megapascal. Now you reach 99.6 degrees Celsius. You are still heating it. Once you reach 99.6 degrees Celsius, you have reached the vaporization temperature. Now at this point, any more heat addition, no more sensible heat transfer will take place. No more sensible heat transfer. Meaning, any more heat transfer taking place to this particular vessel will not cause a change in this temperature, but rather it will cause change of phase. So a change of phase, temperature remains fixed. This statement, is it always true? This statement, is it always true?
Sir,
And the
I think
answer
it will
is,
be true at
yeah.
boiling point.
No, that is okay. We are at the boiling point. At any phase transition, not just boiling, even for melting, this will be true. Even for sublimation, it will be true. Only for pure substance. Okay. It is true only for a pure substance. For azeotropic mixtures or for mixtures in general, the temperature does not remain fixed. The temperature still keeps on increasing. Okay? The temperature still keeps on increasing with a different slope. I will just give you a brief idea about it later on. So there is no more sensible heat transfer. Now here it is still water. There is no vapor. So 100% water, 0% vapor. Now any more heat transfer will cause what? It will cause some amount of vapor to be formed. And now the formation of vapor causes significant change in volume. Why? Because vapor has a much lower density than liquid. Okay, rather we say that vapor has a larger specific volume than liquid, and so any generation of vapor, it causes a larger change in volume. So now say it is still at 99.6 degrees Celsius, is still heating it. So you have water and you have some amount of vapor. You still heat it and it will stay at 99.6 degrees Celsius until what? Entire water liquid changes to vapor. And so when the entire water changes to vapor, right? When the entire water changes to vapor, the volume will increase like this. So this is entirely vapor, but still the temperature will be 99.6 degrees Celsius. Now the last liquid drop has been converted into vapor. Now what happens when you heat? Now again the temperature will sensibly rise, meaning you are now superheating the vapor. Okay. Any more heat addition, it will be tantamount to sensible heat transfer, and now you are raising temperature of vapor, meaning you are essentially superheating the vapor. All right, so this particular point, when you are at the boiling point, this is, and you have only water, this is called as x equal to 0 quality. All right, and this is known as saturated liquid. And at this point where you have 100% vapor, this particular point is called as saturated vapor. And so all the points at 99.6 degrees Celsius, that is at the boiling point, all the points throughout this cycle, or not this cycle, throughout this process, they are set to lie on the saturation curve. Before this, we say that the water was subcooled because it is at a temperature lower than this temperature, and this temperature is correspondingly known as the saturation temperature. And this saturation temperature is at that particular pressure, and the pressure is 0.1 megapascal. Okay, so let me redefine. So the quality X is equal to mass of vapor divided by mass of vapor plus mass of liquid. And this quality is only defined at saturation. meaning it does not make any sense for us to define the quality for fully vapor region, meaning if it is superheated vapor, then this does not make sense. It also does not make sense when you are a subcooled liquid. Any doubt so far?
So like, can you not define X for superheated papers? Like it will be only one, no?
Yeah, so beyond that, it does not make sense. And we will come to why it does not make sense in a while. Because you have already specified it is superheated. Suppose someone says, tell me the quality of superheated steam. You should immediately say that since it is superheated, I know that it has gone beyond its saturation temperature. So it obviously is not in saturation anymore. So I should not define it. It is obviously beyond a point where it was 1. But it is fully vapor now. So it simply does not make sense to define it. I'll come to that point in a while. Let me just draw the curves and I will exactly pinpoint why it is not necessary. So now I would like to tell you this particular diagram that I had drawn, but I would like to fetch this particular diagram from EES. Okay, I don't want to hand draw it. I would like to fetch this particular diagram through EES. So let me do that. So let me share my entire screen. Uh, screen. Let me know if it's visible.
Yes, sir. Yes, sir, it's free.
So yeah, let me fire it up. I'll also work with the free version. If you have installed the free version, feel free to do it along me. If not, it's recorded. You can do it at some other time. So you just fire it up. You get a window like this. It says it expires sometime. Okay, anyway. Mm, yeah, okay. So let's create a new file. Let's create a new file. Let me just increase the size of the font. Let's go to preferences, increase the size of the font. Okay. So first, because we are not bothered with anything, we'll just go to property plot. Inside plots, there is property plot. You click on property plot. You go to Steam. All right. In Steam, you have various kinds of diagrams, and we are more interested in the TV diagram, temperature versus volume diagram. And if you look at the information below, it says include lines of S equal to this, S equal to this. So it means he's asking you whether I should include isentropic lines, and we'll say no, we're not bothered about them right now. And this says include lines of P equal to 20,000 kilopascal, 7,000 kilopascal, 3,000 kilopascal, 8,000 kilopascal. So these are basically isobars as drawn in the TV diagram. Is it clear? Just let me know if whatever I just said is not clear. In the TV diagram, I would also like to draw isobars. So instead of this 20 megapascal, I will draw directly the 22 megapascal because that is like the critical pressure. So let me just draw it and then we can discuss it. Okay, I'll just click on OK. So show lines of constant quality. I don't want that. I will click on OK. So this is the kind of figure I get. This is the kind of figure I get. So what I will do is I'll take a screenshot of this and then we can discuss it. So what was the shortcut? Control Shift. Print screen was it? No. Was it Control Alt print screen? Nope. I just typing. Okay. Yeah. My home PC does not have a SSD, so you have to bear with it. Right. So let me paste it over here. Very good. Just a moment. So what do we see in the TV diagram? What do you call? So this font is overlaid on the top. So this actually goes like this. So what do you call this point? This point is known as the
Critical.
critical point. Very good. And this black curve is known as the saturated liquid line. Okay, saturated liquid line. And this black curve over here is known as the saturated vapor line. I mean, we call it line, but it's more of a curve. So if I were to draw it in pink, you have so you're drawing temperature versus volume. Below this, what was happening is you had water somewhere over here. Now you're heating the water. Now think back to what I just mentioned a few minutes earlier. When you heat water, the temperature increases, but the volume does not increase a lot. But we are in the log scale. Look, on the x-axis, we have a log scale. So this will look something like this. Okay? The slope of the curve is such that the volume change is not that high. So all the curves on the left side will have very steep slopes because the temperature rise will be there. The temperature rise will be there, but the volume change has to be marginal. Is it clear why this slope has to be steep?
Yes, sir.
Because T rises, V not so much. Okay? Then you hit the temperature where you have initiation of vaporization, but still everything is liquid. Okay? This is this point, suppose I call it A. So at point A, everything is liquid, but any heat transfer causes vapor formation. So then if you keep adding heat, you are now sliding along this curve. So at this point, you have x equal to 0. Slowly you are generating more and more vapor. You are traveling along this curve. You keep traveling up until all the liquid gets converted into vapor. So at this point, you have x equal to 1. That is, you're still at the same temperature. You're still at the same temperature. And all the liquid has been converted into vapor. So at point B, A and B at same temperature, and that temperature is known as the saturation temperature. We call it Tsat, and that Tsat is drawn for a pressure of 20 kilopascal at 20 kilopascal. Okay. Now, after reaching point B, at the same temperature, at point B x equal to 1, all liquid converted into vapor. Now, suppose that we are at point C. Now, what happens? Look, any further change, any further increase in or addition of heat, what does it do? it causes an increase in temperature and increase in volume. Okay, it causes both increase in temperature in going from point B to point C. We have an increase in temperature, obviously, because the y coordinate is temperature, and we also have an increase in volume, obviously. Why? Because the x-axis is the specific volume. Now, what happens for 22 kilopascal? You see that you are going from this liquid. So for 22, you're going from liquid, and there is no sort of transition from x equal to 0 to x equal to 1. You're simply going whoop, it's simply going up. So you're smoothly going from, in fact, let me draw another ISO bar for say 30. We go to plot, property plot. I will draw for 30 megapascal. Okay. So you see the 30 megapascal line, it will never go into the dome. Do you see the point? Meaning it will go from liquid water to vapor without actually going through this. So there is no demarcation between liquid and vapor at that point. That is why we say that we are beyond a critical point. Okay.
So here discontinuation, what it means, sir? Like
The database does not have the data to plot it.
okay,
No
sir.
other interpretation should be made of it. But in reality, it comes like this. I mean, it tries to go parallel to this uh, curve over here, this black envelope.
So is that vapor or water? Like what state is in it? Like it's
So
difficult to
that's
understand.
you don't call it, you just call it steam. At such a high pressure, even if you have water, you call it steam. Rather, you call it supercritical steam.
Okay, sir.
You will not be able to make the distinction whether it is liquid or gas or what it is. And supercritical substances are quite important. In fact, we have a project running on supercritical carbon dioxide. So whenever you can hop down to the lab, I can show you the apparatus. It's quite grand. Okay. All right. So this takes care of this. Let us proceed. So now, if you're doing calculations by hand, how do you find out the specific volume of this pot, of something in middle? The engineers have sort of documented. See, because this volume you can find out using experiments that, okay, 100% water, 0% vapor at 99.6 degrees Celsius. You started off with 1 kilogram of water. Now, because you can calculate this volume, you will now know that what is the specific volume at x equal to 0. At x equal to 0, the specific volume, we call it VL. That is the specific volume at saturation. Customarily in Sontag, they use VF, that is fluid. Now, at this point, when x equal to 1, also you can figure out the volume. So you will be able to find out Vg, that is the specific volume of saturated vapor. Now, how do you go about finding out the specific volumes of everything in between? So follow closely the chain of logic. Basically, you want to know over here or over here or over here. Basically, anywhere inside the dome, you are interested to find out the specific volume. So the logic is the total volume occupied in the piston cylinder arrangement is because of the volume of the liquid plus the volume of the vapor. So in Sontag's notation, we can write this as Vf plus Vg. Now, according to the definition of specific volume V is equal to the total volume over mass. So what that means is I can write the specific volume of the fluid is equal to the volume occupied by the fluid divided by the mass of the fluid, and similarly I can write down the specific volume of the gas will be the volume occupied by the gas divided by the mass of the gas. So if I make this substitution, so total volume is specific volume times the mass. So it is Vf times Mf plus Vg times Mg. Okay, this is the total volume. Now if I were to define average specific volume V of the entire system, what would it be? It would be the total volume under consideration over total mass. So therefore, combining this and this, I can then write down, or I mean, I can, anyway. So what is, I can simply substitute this over here. So we have small v is equal to Vf Mf plus Vg Mg over M. Fine. So what does this become? This becomes Vf Mf over M plus Vg Mg over M. And if you recall the definition of the quality, it is the mass of the vapor divided by the total mass. All right. So what can we say about this expression? It's going to be Vf. So in terms of x, what can I write Mf up over Ms?
1 minus x.
1 minus x.
It will be 1 minus x plus Vg times x. So essentially, I can write this down as Vf plus x times Vg minus Vf, and this is more broadly written as Vf plus x Vfg. So if I specify, so let me just write down the expression. So V is equal to Vf plus x Vfg, where we recall that Vfg is equal to Vg minus Vf. So at this point, suppose the x is equal to 0.2, I just need the V at A, meaning Vf. I will just need the V at B, meaning Vg, and I simply first find out Vfg, that is the difference in the specific volume between saturated vapor and saturated liquid, right? And I will simply multiply it by the quality and add it to Vf. So it's like a linear interpolation. It's literally like a linear interpolation. Is it okay?
Yes, sir.
I mean, so far we have not done something very sacrosanct. Okay, so let's proceed. So you can alternately also draw this on a, might be a bit difficult for you to visualize at this junction, but it's not super difficult. So we will try to draw the pressure temperature diagram for such a fluid. And let me first draw the diagram and then we will discuss about the specifics. It looks like a Y, and after a point you reach the critical point and there is nothing. Okay, so this is the solid phase. There is the liquid phase. Oh, sorry, the liquid is this one. So in going with an isobaric process, okay, if you go at an isobaric process at low pressure, yes, at low pressure, an isobaric process. How does an isobaric process look in the PT diagram? It looks like a horizontal straight line. So if the pressure is low enough, you will simply go from solid state to vapor state, rather volume, solid phase to vapor phase. You have to use all the terms correctly. This particular process is known as sublimation, right? And so this curve is called as the sublimation curve. If you go at a high enough pressure, if you go from solid, if you keep adding heat isobarically, meaning the same piston cylinder arrangement, if you add heat isobarically, what will happen? You go from being solid to first a liquid, then from liquid you transition into vapor and so on. Okay.
So this sublimation, can it be done for any pure substance or like very few?
It can be done for any pure substance. This curve exists for any pure substance. This is not just specific for water.
But so like, can you give like range for like how much less pressure we need for water? Like water can't be directly evaporated.
So the critical temperature of water. Okay, we'll have to look at the properties in ES. I don't recall the properties. Yeah, we
Okay,
can figure them out.
So excuse me.
Yeah.
So what is the reverse process from vapor to solid called? Is it called the same sublimation or is there any other term?
I've never thought about it, but I mean, you could call it desublimation. I don't know. But yeah, I mean, I never thought about it.
Okay, okay.
Yeah. So yeah, where was I? So when you heat this, uh, so you're going from solid to liquid to vapor. Now you will say that, but where did that whole saturation curve go? Well, the saturation curve, where has it gone? Who can answer? The saturation curve, where has it gone? Meaning, what I'm talking about is you're staying here for a long time. Where is this business going? Where has this business gone? Over here?
So there we were plotting TV curve.
Yeah.
Here it is a PT curve.
Yes, good observation. So if I were to draw a three diagonal plot, three-dimensional plot, I don't know what I'm saying. In a three-dimensional plot, if the third axis is the volume, then you would go along the third axis. So this line that you see, yes, it's just a projection. Do you understand what I mean? So I will make it complicated in a while. I will make it complicated in a while. Thank God this will be recorded so people can watch it over and over again. But it's not so simple to grasp in one go.
Sir, is the 3D picture available?
I will try to draw it with all my drawing skills or the lack of it, whatever. I will try to manage some scans also. I don't know, but it is when we start to or when we try to at least draw it, it should be clear. I mean, hopefully it should be clear. Okay, when the pressure increases even more, when the pressure increases even more, what happens is you go from solid to liquid, and once you're in the liquid, you go from this liquid phase to the vapor phase, but you're not really going because after this point, this is the critical point. There is no real distinction. So you're simply in the liquid vapor phase. Okay. So how much is this pressure? We just looked at the value. How much is this pressure?
22,000
22.
kilopascal.
So it's 22, approx 22 megapascal. Beyond 22 megapascal, you will have this. So this curve is known as the fusion curve, and this curve is known as the vaporization curve. And this is the critical point. And there is this point. So if you are able to maintain the pressure and temperature precisely at this point, right, you get what is known as the triple point. And for water, the triple point is at a temperature of 0.01 degrees Celsius, and that happens at a pressure of 0.6113 kilopascal. Yeah, so there you go. You have your answer as well. So any pressure below 0.6113 kilopascal, okay, any pressure below 0.6113 kilopascal, if you start off at a lower temperature and if you heat it, so this point, so this thing is at 0.01 degrees Celsius, and this is at 0.6113 kilopascal. Now, if you were to take water at maybe minus 10 degrees Celsius at a pressure of say zero point 0.1 kilopascal, and if you were to heat it, you would simply go from like ice to vapor. There will be no liquid. You will not feel that wetness. All right.
Yes, sir.
All right. Perfect. So now let us try to make it a bit more complex. Before making it a bit more complex, yeah, in fact, let us do the complexification thing first, and then we will come to the independent properties and also. Let us try to draw it. Let us just try to draw the single branch. We'll see what happens. Wait, am I at the end of the page? No, I'm not at the end of the page. Let me just zoom out a bit. So what do we have? We will have P, T, V. On the third axis, we have the volume. And so let me first draw the projection on the PT plane, and then we will see actually in the third axis how it should have looked. So let us just focus on uh, this vaporization curve for now. Let us focus only on the vaporization curve for now. must realize that this is just the projection that you're seeing on the PT plane. This curve is not actually flat. This is the critical point. You agree with me on this? This is not the actual curve. This is just the projection you see because we plotted the same on the PT curve, meaning you're looking along the V-axis onto the PT plane. First of all, this much is it clear?
Yes, sir.
Yes, sir.
Okay. Now, let us see what happens. So, when we looked at the projection in the TV plane, what did we see? In the TV plane, we saw this entire dome business going on, right? So, this critical point, I mean, so in the TV plane, we had something like this. This is the projection. This is again the projection of something. And at a given pressure, we had curves. Now the engineering drawing is going to be tested. We had curves like this. Yes? I mean, this I'm drawing, these are incorrect, but this is correct. But this was also the projection. You agree with this?
Yes, sir.
Yes, sir.
So now the actual image will look. So it's a project. There is some surface here. Basically, there is some surface here whose projection on the PT plane looks like this, and whose projection on the VT plane looks like this. Uh, and whose projection on the PV plane will look also something like that. And the isotherms will be like this. And the isotherms in the vapor phase will be solely like this, like you would expect for an ideal gas. So this is in the PV diagram. This is in the PV diagram. How will they look? I don't know. Okay, let me just. I mean, this much is clear, right? This logic is clear. So let me now draw another diagram. I mean, someone has done it way back because someone had that much intuition and grasp. I was. So basically, you have a dome like this. You have pressure, volume, temperature, and how do I justify? Yeah. So on this particular axis, you have not on this particular axis. Hang on, let me just try to grab it's easier to discuss the surface directly. One moment. Either it has to be drawn with the help of a PC or it's simply, I mean, horrendous to just even try to do it. We will search for PVT surface or water. Okay, there it is.
Yeah, is your screen shared?
No, I'm looking for the thing. I found a very nice image. One moment. I will bring it to the desktop and again show you. Don't worry. Okay. So on the z-axis you have the pressure, on the x-axis you have the volume, and on the y-axis you have the temperature. So if you take a slice at a certain pressure, so how do you get the VT plot for different pressures? How do you get the TV diagram for different pressures? So this is at one pressure, this is at another pressure, this is at another pressure, this is at a higher pressure,
So
higher
we
pressure.
compress it axially downwards.
No, so you just take a bunch of slice cuts. In which
Yes.
direction? So
So the
this
plane should be parallel to the
VT plane.
volume temperature.
The plane should be parallel to the VT plane. That's it. See, you can take, suppose this pressure is at 20 kilopascal. Meaning, if I stay parallel, so wherever this surface is now cutting this 20 kilopascal line will give me the appropriate diagram. Is it okay? So wherever this diagram intersects this surface, so for example, it is intersecting here. It will intersect like this. You see my point, right? It will be like this, then this. We are looking at it in the TV direction. Okay. Anyway, it will be like this. So you just need to find out the intersections of this surface with the isobar. So suppose you now want to know how does it look for 100 kilopascal. So you just select 100 kilopascal, draw a plane parallel to the VT plane through this 100 kilopascal, and you will be able to find the curve. Now what happens at the critical curve? The critical curve, what happens at the critical curve?
So there will be peak, like there will be only one point.
Yeah, so the 22 megapascal plane, 22 megapascal plane will just intersect this curve at this point. The plane will intersect this surface only at this point. Is it okay? I mean, it
Yes,
will
sir.
intersect the points behind as well, but it will no longer intersect this liquid vapor phase, right? Anything more than 22 megapascal, it will simply go beyond this point. Okay. So it is a bit complicated to visualize all this. There's an entire set of theory called as the cathedral theory, which helps you to make these surfaces, which is beyond the scope of this course. That is a bit of advanced stuff. Essentially, you have these kind of surfaces which you have intersections on, and we are just bothered with the projections of those surfaces. But even what Venkat said, that you squish them to get this, that is also correct. This is just, I mean, looking at it from the axis perpendicular to the p-axis, you're simply squishing everything down. But each of these curves are basically from intersections of the p equal to constant plane with the surface. Okay, you have this surface that is marked over here. Let me just get a colorful one. I think hopefully this. So you have the light pink surface, and you just sort of take intersections of a surface. So I mean, what is an isobar in this? What is an isobar in all of this? What is
So
an isobar?
parallel to
Plane
VT.
parallel to
VT. So when you just take a slice cut of that isobar with this surface, this entire surface, you will get those curves that we're talking about. Okay. At a certain point, at a certain critical point, you will not be able to intersect the vapor liquid dome anymore, and then you will not have the curve. Anyway, for our purpose, this discussion itself was a bit too much. We did not need to discuss this. Our discussion could have been restricted to only this point. But still, I just wanted to show you how they look like. In hindsight, maybe not such a good idea. Even people have even tried to do it. I mean, they get an A for their effort.
In the EES, is it not the
No, no,
facility
the
is
3D plot CES does not do. 3D plots it does not do. It's not meant to be used that way. Okay. All right. So let's proceed. I mean, this is not what we have. How much time left? We have around 40 minutes left. Good. So now we will move on to determination of properties. We will move on to the determination of properties. But before that, independent properties. Independent pure substance. Someone is saying something on chat. Okay, someone has done it 3D, has it? Let's see. Is it available for free? Okay, there you go. Is this for 3D printing? Ah, okay. So, in fact, I'll 3D print this today itself if I get the chance. So look at this. We are bothering more about the liquid and vapor. Are you able to see the screen?
Yes, sir.
yes, sir.
So you are now focusing on the liquid plus vapor. You have what? You have liquid, liquid vapor and vapor. And now you imagine you're looking at the curve like this. You're looking at the curve like this. So what do you see? Can I change the lighting of this? Can I change the lighting of this? Things, textures? No. Can I change the lighting? If I were to change the lighting, things would become much better. But is this an STL file?
Don't know, sir. I just searched it on Google and I found.
Can I download it? No. I have to log in to download. Okay. But wait. If it's there on Thingiverse, we're doing a lot of efforts to just visualize it, but anyway, I don't know whether you're able to see this solid or not. There's a solid, liquid, and gas. So this surface you see on the projection. So now we are looking at the PT diagram. Okay, this is now the PT diagram, and you have the solid to vapor curve, which is the sublimation curve. This is the sublimation curve. Hello.
Yes, sir.
Yes, sir. Yes, sir. In the
Then
Y
you
shape.
have the fusion curve where you're going from solid to liquid. See this one.
Yes, sir.
And then you have the liquid to gas, this one, the vaporization. And at point 1, see, we had a broken curve at point 1. This was the critical point. Okay, so at 1 you have the critical point, so you are no longer demarcating between liquid and gas. So this curve stops over here, and you simply have a transition between liquid and gas. Okay, you simply have a transition. This sharp curve should not be there. Probably to make the STL file it is there, but this should not be there. Okay, you simply go between liquid and gas. Now, if I were to look it in the TV diagram, in the TV diagram, you have liquid, then transition from liquid vapor, and then gas. Okay, up until you reach point 1. So now point 1, so now we are looking at this slice. So if you're fixed at this pressure, suppose you're fixing yourself on this pressure where 4 and 3 are, then what happens? You take a slice between this. When you take a slice along this plane, which encompasses points 3 and 4, you get any curve like this. Okay, you will get a curve like this. So 3 and 4, they will give you this straight line. And this curve that you see, that is the intersection of this plane with a curve. Is it okay? Man, I really wanted the STL file that I can. What do I have? Wait, we will look at this. Does anyone have a Sketch5 account? Where can I download? Where's the download button?
Sir, in the
Hmm?
model information, it is mentioned it is STL file.
Yeah, but so I need to log in, do I? I'll just log in with my Facebook. Okay. So where do I Okay. Does anyone know where do you download this from? I can't seem to find it. Is it just me or is no one else also getting the download link? Or do I need to buy this? Okay, I don't have it. But anyway, you need to, I mean, if someone gets the STL sometime, if you take a cut, you will get that upward rising slope because there's a upward rising slope like this. I mean, if you're good in engineering drawing, you will be able to get it. Venkat, how do you download from this? You don't know because you're also new to this site.
Sir, I found another site and I put it in chat. There it is. A free download is available.
It was there on Thingiverse. So we just need the STL file. Let's see. I mean, we have enough time in the course. It is worth our time to just look into this. Or it will open it in Cura. I think it may be okay in Cura also. Let's see. We'll simply slice it and then we have the vertical slices. I think it should be okay. Ooh, it's a big model. So let's scale it down. Let's rotate it. All right, let's slice it. Let's preview it. All right, so now we're taking the vertical slice. Now look at this curve. You see, you're coming from liquid to the saturation point, then you're holding it, and then you go to this curve. Now, are you convinced?
Yes.
You're going from liquid to the saturation point, then you're in the liquid and vapor zone. So you go straight, and then you're in the vapor zone. And now, if I go to a higher pressure, you see how the dome is shifting up? So liquid to saturated liquid, subcooled liquid to saturated liquid, then you're inside the dome, and then you go to superheated vapor. If I keep on increasing the pressure, what will happen at a certain point? What will happen? The two curves have mixed,
Endpoint.
and there is no more distinction because you are now beyond the critical point. Okay? Is everyone convinced now at least?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Okay, that was a lot of work, but yeah, I mean, thanks a lot. So now you have this sublimation curve. You go from solid to solid plus vapor. So there is an equilibrium between solid and vapor also. And then you go to superheated vapor. Okay, you go straight from. Now you might be thinking, this diagram is only for steam. Huh? This diagram is only for steam, meaning when the temperature reduces, when you go from liquid to solid. Why was I able to say that it is for steam? You have on the y-axis the temperature, or rather in this axis you have the temperature. So what happens? You have liquid over here and you have solid over here. When the temperature reduces, when you're going from liquid to solid, what has happened to the volume? What has happened to the volume? When you're simply reducing the temperature, you're going from liquid to solid, right?
Yes, sir. There is a slight increase in volume in the between.
So that increase in volume is because of the anomalous property of water.
Anomalous expansion.
Yes. So that is how I could say that this diagram is made only for water. Okay. But for any other material which sort of contracts on cooling, this wedge that has now come to this side, this wedge, okay, it would actually go on the inner side, nothing else. All right.
Yes.
No, I want to hear it from everyone. I mean,
Yes, sir.
Yes, sir.
it's just that this wedge would go inside because the volume would reduce as the temperature is reducing, as you're making that phase transition, nothing else. So the usual suspects have answered, but I'm not getting an answer from everyone. Maybe it's a lot of overload. Maybe I'm mistaken to take constant classes. But what we can do now is we can take a 5-minute break and we can reassemble. You should stay online because we're gonna find out some properties, do some calculations now. Get your calculators ready. But you know what I will try to do is I will try to break this STL into multiple layers, like 3 layers. One for this, one for this, one for critical. I will try to make it stackable. This would be a good addition to as a teaching tool. This is fantastic. 3D printing, yeah. You could also do it in SolidWorks. In SolidWorks, you just import this guy. It should be, in fact, better visualized in SolidWorks. Let's see. So you have this. Very good. So now, how do you make that plane cut? I think it is. Oh no, it is in features. No, not in features. Evaluate. It's not, definitely not in evaluate. Anyone know how to do that cross section? Is it this one? Yeah, it's this one. So I will simply rotate this. I will make this 90 degree. And I will make this. How do I offset it? Someone needs to help me out over here. You go for the reference plane and How do you move this along? You don't move it along, is it? Let's preview it. Oh, damn it. Oh, I don't know. Does anyone know how to do this? This is how it should have been. No, I don't remember. It is there. That much I get it. But oh, selected bodies. I need to select this body. One. Ah, it's not selecting. Okay. Yeah, the STL. It's not. If I were to select this, then it should have been fine. Anyway, that's a glitch. Who knows? So, crash that. But anyway, I mean, I hope this 3D printer slicer could resolve your issues. So just take a 5-minute break. Do you have a class from 11?
Yes, sir. Two
Yes, sir,
students
we
have.
have class.
Okay, so just take a 3-minute break and just get some tea. We have 20 minutes still there. So I'll be back. for sticking around. Skip this. So for a pure substance, you need two independent properties to specify its state completely. Okay, so in the TV diagram, so suppose someone were to say that what are the two independent properties over here? Obviously, I can say it is some temperature, some specific volume, or I can say it is some temperature and some pressure also. Why? Because this temperature is unique and this isobar is also unique. Remember that in the TV diagram, this is the isobar. This is how the isobar looks like in a TV diagram. Okay, or I could specify the V and P also. Okay, because this is unique. Similarly, in the subcooled region, so this is true for the superheated. I mean, there are other properties also, we'll get to them later. In the subcooled region, you can also specify any of the three combinations, TV, PP, VP, it will all work. But what about inside the dome? See, this isobar, this is the isobar. Now, inside the dome, the temperature is fixed and the temperature is Tsat. The pressure is also fixed because the pressure is the isobar. So I will call it Psat. Now, given a certain isobar, listen to this very carefully, given a certain pressure, I automatically fix up what my saturation temperature will be. And what is that saturation temperature? In this particular case, it is nothing but the boiling point of that pure substance. This temperature is nothing but the boiling point. Is that clear? So given some pressure, automatically T boiling is fixed, meaning Tsat is fixed. So how do I know where I am in this inside this dome? I do not know. I could be here, I could be here, I could be here, I could be here, anywhere. So what helps me to specify that additional? So it means that given a certain pressure inside the dome, that is inside saturation, when the pure substance is saturated, I cannot specify P and T to get the exact state of the pure substance. Cannot be used because they are not independent. They are dependent. Inside the dome, P and T are not independent because given a certain pressure, the T sat automatically gets fixed. Meaning T sat is dependent on the pressure, and so I cannot specify exactly where the position lies, and so I must use the quality as an independent parameter. So inside the dome, I can use pressure or temperature in conjunction with the quality. Is it okay?
Yes. So then
Yes, sir.
indirectly we are using three quantities, right?
No, you are still using two. Either you will be using pressure and quality, or you will be using temperature and quality.
Okay.
It is definitely not three properties, because if I specify the pressure, then the temperature is naturally found out as the saturation pressure at that temperature. Okay.
Yes, sir.
So it is not an independent property. You need independent properties. Now, first of all, do I even have contact with me? Let me just. Let me look up contact. Okay, it's gonna do an index search now. But most likely. Okay, so I have exactly the 6th edition, which is good. So now if we go to the tables, we have now reached Appendix B, which says Thermodynamic Tables. So let us see, what do we have? Table B.1, Thermodynamic Properties of Water, Saturated Water. Under saturated water, you have a whole lot of temperatures, a whole lot of pressures, a whole lot of saturated liquid specific volumes. So these three are saturated properties. So let me take a screenshot and we can discuss it over there. Okay. So what do we have? For saturated water, what are we looking at basically? You're looking at this curve. You're looking at the saturated water tables, and so you're looking at this curve inside. Okay, so here you have two kinds of tabulations and I will go through them. The first kind of tabulation, so this particular B.1.1 is increments of temperature. Increments of temperature. Meaning temperature is jumped by 5 degrees at a time and correspondingly all the properties are marked. So you have, if I were to graphically depict it, suppose this red line is this 5 degrees Celsius line, right? So the next entry, 10 degrees Celsius, would be over here. Then the next entry would be over here, and so on. Okay, just trying to give you a broad idea of how the lines actually look like. And so corresponding to this, what are the properties that I have? So at 5 degrees Celsius, it, it tells me that the saturation pressure corresponds to 0.8721 kilopascal. Meaning, what does it mean? What does it mean when it tells me that at 5 degrees Celsius, the pressure is this? How do I graphically depict it in the TV diagram? In the TV diagram, how do I graphically depict it?
So the red line is
The red line will be
zero
at
point
0.8
eight
Yes.
pressure.
So
towards
this
us.
isobar is 0.8721 kilopascal. And if I were to draw the entire isobar, it would look something like this. Do you agree?
Yes, sir.
Good. Now it says saturated liquid. So we now have the entries of specific volume. We have 1, 2, 3 entries. So the first entry says saturated liquid. VF, specific volume of saturated liquid, is 0.001, which is the inverse of it is 1000. So the density of liquid is 1000. So it tells us, if I call this point small a and point small b, at point small a, V is equal to 0.001. At point small b, it is what? 147.11. At point B, V is equal to 147.118. Alright? And it additionally gives you the VFG value, which is simply Vg minus Vf. This is the difference between this and this. Why have I tabulated it? Because we have seen that in order to find out the property at any internal point, you simply can take this value, add it to VFG times the quality using this formula that we have written now. Okay, that is why the people have already tabulated it for you. You don't need to do that extra step. To the right of specific volume is internal energy, which we don't need to worry about right now because we have not yet covered that. But you can see they are having a similar tabulation. You have internal energy of the fluid, that is internal energy at point A. You have internal energy of the vapor, which is internal energy of point B, and you have the difference between the internal energies, UFG, which is UG minus UF. Any doubt in this so far?
No, sir.
Sir, excuse me, sir.
Yes.
Sir, the graph which you have drawn, is it specific volume or volume?
Specific volume. There will be no absolute quantities over here.
Okay, yes.
Okay, so let me go back to the PDF. So this table keeps on going. You reach very high temperatures and you keep going until where? Until, so you see, I mean, okay, so this particular page, if you actually have the Sontag in front of you, this page will tell you at these temperatures and pressures, this is specific volume, internal energy. The next page is actually enthalpy and entropy, but at those same temperatures and pressures. I mean, are you able to understand what is going on? The left page is this and the right page is this. So in a single open of a book, you will be able to get the properties of specific volume, internal energy, enthalpy and entropy. Let me try to show it in an actual physical book how it looks like. Yeah, am I visible?
Yes, sir.
This, is the book visible or not?
So there is more brightness.
There is more brightness. Now,
Yes, sir. It's visible.
Yes, sir. Yeah, yes, sir.
so this particular page is the specific volume and internal energy. This specific page is the enthalpy and entropy. On the left, you have all the temperatures incremented by 5 and the corresponding pressures. And then the enthalpy tabulations, entropy, volume tabulations. Then you have, what is it? Internal energy tabulations, then enthalpy and entropy. Okay?
Yes, sir.
sir.
Oof. So if you can focus your attention on the screen again, so you will see that you will go up to a pressure of almost 22.089 megapascal. You're increasing the temperature. Look, you're increasing the temperature slowly at 374.1 degrees Celsius, which corresponds to an isobar of 22.08 megapascal. You have the critical point. Okay, so you have all the four properties. Now you have saturated water with pressure entries. That was saturated water with temperature entries. What is the difference between the two? In this, instead of temperature being stepped by a fixed amount, you are now stepping through pressure in a fixed amount. So let me take a screenshot. Let me grab hold of this. Where is it? Oh. So this particular, so like I said, there are two kinds of entries. The previous entry, you see temperature was incremented by fixed amounts and everything else was tabulated accordingly. But now pressure is incremented by fixed amounts and temperature is and everything else is tabulated accordingly. Is the difference between the two clear first of all?
Yes, sir. The independent variable is same.
So you can now draw the PV diagram. We had drawn the TV diagram, but now you can draw the PV diagram. And how does the PV diagram look like? So isotherms in the PV diagram, they look like this. So now, if you look at say 50 kilopascal, so suppose this is 50 kilopascal. So this is fixed and it corresponds to a saturation temperature of 81.33 degrees Celsius. So it means that this isotherm, this particular isotherm is how much? This isotherm is 81.33 degrees Celsius. Is it okay?
Yes.
Yes, sir.
It should be, I mean, there's nothing difficult about it. So yeah, that's how it looks like. I mean, just to quickly give you a glimpse, I mean, we'll continue obviously in the next class. We're out of time. So let's just see certain things. So suppose you want to know the specific volume of water at 50 degrees Celsius, a specific volume of vapor at 50 degrees Celsius. Okay, so you say V1 just let me, so I will say V1 equal to volume steam T equal to 50 x equal to 1, meaning I have specified the two independent quantities, temperature and quality, and I'm fetching the specific volume. So the keyword is volume. So I will simply run it. I will simply click on this solve button and I will get 12.03. What's going on? Volume of steam.
Sir, it is 50 kilopascal. The pressure is
The pressure is 50 kilograms. Oh, so I will simply make this change. Okay, I get 3.24. Very good. I get 3.24. Now, suppose you say you want to actually plot this. You want to plot this in the TV diagram. You you want to plot this point on the TV diagram. So I will first fetch the temperature also. Temperature steam P equal to 50, x equal to 1. I should fetch this. So what do I get? T equal to 81.32 degrees Celsius. It says 81.33, close enough. In fact, what happens when I change x to 0.2? What do you think will change? Will the temperature change?
So volume changes,
Yes,
temperature
sir.
is constant.
No, sir.
Very good, because we are inside the dome. And inside the dome, regardless of the quality, the temperature and pressure, they stay fixed. Yes? The volume will change. You're correct. But anyway, we just wanted to fetch the property. So I will just go, I mean, you can let it stay like this. So then we go to plots, property plot, we go to steam, TV diagram. We don't want to include any isobars except maybe at 50 kilopascal. Okay, we click on OK. We get this curve. Then we go to plots. Then we go to overlay plot. Then on the x-axis we have the specific volume. On the y-axis we have the temperature. We will mark with a solid marker. So in the program, I have basically click on OK now. So you get the point over here. Okay, so basically in the program, I have put the volume and temperature in arrays, and I'm simply plotting the array points, nothing else. I mean, more on this throughout the course. I can make this 0.2, 0.2. Let me run it so that the array values are updated. I will go to plots, overlay plot. On the x-axis, we have the volume. On the y-axis, we have the temperature. So this is the point where the quality is 0.2. Okay, so you can see that there are big leaps in quality when you're going in the log scale. Why is there? See, you would expect this to be at a higher quality, but this is just 0.2. Why is that? Because it's in log scale. Okay, so in the same plot, that is why they also say, should I also plot lines of constant quality? If I say yes, so if you look at this particular line, are you able to see it? This particular gray curve is the line of ISO 0.05 quality. Yeah, this particular line is the line of ISO quality 0.1. This particular line is the line of ISO quality 0.2. This particular line is the line of ISO quality 0.5. Is it okay?
Yes.
Yes, sir. Yes, sir.
So where can we find the tutorial of using this EES platform, like the syntax, all those things?
Well, I don't know where to suggest you to look at, but I will shamelessly say that when I had first taught this after joining here, I had made almost 50 videos on EES where I have solved a bunch of problems from Sontag. So you can have a look at those. Some of the videos are also there on my NPTEL course. So you can have a look at those as well.
Sir, in
Yes,
the
sir, thank you.
TV, sir, in the TV plot, can we take volume as a independent parameter because that can help us inside the dome? Can volume be considered like volume and temperature to be two independent parameters?
Yes, volume and temperature can be two independent parameters.
Okay, sir.
Volume and temperature can definitely be two independent parameters. Nothing wrong in that. I had mentioned this also. So see, quality is also a proxy for volume because once you know the specific volume inside the dome, you can also figure out what the quality is, or vice versa. Once you know what the quality is, you can figure out what the specific volume is.
Hello,
Okay.
sir.
Yes.
So we have another class. Can we leave?
Yes, 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 you can. So we'll see each other on Wednesday.
So thank you, sir.
Right, so take it easy. Still, we haven't done something very useful. We have not solved problems. That starts on Wednesday. Okay, bye.
Bye, sir. Thank you.